Hey everybody, welcome to Altium Academy. I'm Zach Peterson, I'm a technical consultant with Altium, and today we're going to talk about copper roughness. Now, why are we talking about copper roughness again? Well, we got a viewer question asking about copper roughness and specifically how it affects your impedance, and it really helps to know intuitively how this all works. So that's what we're going to go over today. Let's get started. When we look at the metal that's on a PCB, it's essentially just a copper foil. And copper is inherently rough when it's on the surface of a PCB. There are a few reasons for that. One is just the particulate structure of the actual copper, and I'll show some SEM images in a minute that actually show what this looks like at a microscopic level. The other reason is that copper is actually intentionally roughened in order to create a strong bond between neighboring laminates when you're building the PCB stack-up. The extent of the roughness kind of varies. Some copper is rolled on or is applied smoother than other types of copper that are applied on the laminate. And so sometimes you have to roughen certain laminates more than others. And so it's all about kind of balancing, do we need smooth copper to ensure low loss versus we need to have some roughness in order to ensure that the two layers bond together. So before we get started, we want to look at a viewer question real quick. Rudwij Mullier writes, hey, can we get a video on copper roughness and change in impedance profile? So what this question is referring to is exactly how the copper roughness introduces, number one, a change in impedance in your impedance profile, but also how it introduces loss in your impedance profile. Okay, so the first thing that we want to do when we start talking about copper roughness is really think about what the cross-section of the PCB looks like, and then exactly where the roughness plays a role. So generally when we look at copper roughness, we're actually looking at the roughness of the trace up here rather than looking at the plane. Now, the plane roughness does also play a role, and there's actually a really recent article in Signal Integrity Journal that looks at this. I encourage you to go read it if you're interested in learning more about this. Now, copper roughness generally exists around the edge of this trace. So it's due to the plating, as we've discussed in a couple previous videos, but it's also due to intentional roughening, as I just mentioned, for manufacturing purposes. It's also due to the fact that this surface here, so this green surface, is already rough, okay? And so because we have the ground plane here, and then we have our electric field lines essentially, terminating like this at the nearby plane, we have some charge that tends to get clustered around here. As the charge moves along the trace, and I say moves with big quotation marks because the charge doesn't really move, but as the charge is essentially propagating along with the signal on this trace, what happens is it encounters this rough interface around the edge of this kind of rectangular trace that I've drawn here. The charge wants to cluster around the edge because of an important effect called the skin effect. So if you've ever taken an electromagnetics class, you'll actually have the pleasure of deriving what the depth is here into this trace, where the charge basically clusters along the surface, okay? So this is called the skin depth. And so because this is not perfectly smooth, you actually have some interfacial resistance between all of the different particles that make up this trace. And so it's that interfacial resistance that then gives you some additional impedance when the skin effect happens when a signal travels along the trace. So now we kind of know why this happens. It's essentially a consequence of Maxwell's equations, and again, you can calculate what this is, but now we actually want to look at what happens in terms of the impedance. So this is kind of a subject that's near and dear to my heart in interconnect design. So first things first, we're just going to write out what the typical equation is for impedance with losses. So omega here is the angular frequency, here I is the imaginary constant, R is the DC resistance of this trace, and then G here, G is related to C, but it also accounts for the loss tangent. Together, these account for the loss tangent in the dielectric substrate. And so just looking at this, you might be inclined to think, well, here I've got some resistance. If this is adding some resistance, it adds it in right here in this R term. And technically it does, but it also creates an additional inductive impedance. So you get an addition to both of these terms, and that increases the impedance. It also increases the losses, because if you want to, and I'll leave this as an exercise for anyone watching, if you actually calculate the propagation constant and take the square root, you'll be taking this thing times this thing. And so if I make this numerator bigger, I essentially get more losses and I get a larger propagation constant for the real and imaginary parts. Take those together and that's how your impedance and propagation constant are affected. In terms of what is the exact contribution to the L term here? So the L term is going to be whatever L is at infinite frequency plus the skin resistance divided by square root of angular frequency. So this is the additional impedance that gets added onto, or I should say the additional inductance that gets added onto the regular inductance when you have roughness in the system. So here we actually haven't even considered roughness. This is just R sub S, which is this skin resistance of this trace. So how do we get to roughness? Well, roughness is actually modeled by looking at how this roughness changes this dielectric thickness, and then we assign an additional factor here that just increases the skin resistance. So that's essentially what roughness does, is it just increases the resistance artificially of this skin effect, or created by the skin effect. And so essentially this would become L equals L infinity plus some K, we call the copper roughness factor, times the skin resistance divided by square root of omega. This essentially tells you everything about how the inductance changes. So the inductance and the capacitance, there are formulas that you can use to calculate it. You can get it from a field solver. There are a number of ways you can get these values. If you actually go onto my channel, I actually show a method that you can use to get all of these different terms without actually calculating them. I know that sounds odd, but trust me. And that will give you the impedance. Now, what we want to look at next is exactly how this K value is defined. This is really the heart of the question. This is where we now have to consider the actual value here of this roughness. And when I say the value of the roughness, I really mean we have to quantify somehow exactly how rough this interface is on the copper as it sits on the PCB. Okay, everybody, so I promised I would show some SEM images of rough copper, and that's exactly what we're looking at here. So here in the top row of images, we have some SEM images showing what copper roughness actually looks like at the microscale, and these are at 2 micron scale bar. In the bottom, you just see the side view, and so this is what you'd actually look at if you took a microsection and put it into an SEM and then took images of it. Here in the top row, you can see all the little particulates. They kind of cluster together in the plating process, and that size of these clusters and the individual particles and their arrangement is what's going to determine how roughness affects the impedance profile. And so to actually model this, we basically use kind of this picture. This picture is essentially trying to model an arrangement that looks kind of like this top left image. I mean, it's a pretty rough approximation, but it just kind of gives you an idea. But this is how you would do it theoretically. So here, you know, we have the height of this stack of particulates, and then we have a radius for this stack of particulates. Basically the way this works is if I have my skin resistance, it transforms into some roughness factor, and that roughness factor is going to be a function of frequency. It's also a function of this height of this arrangement of particles, and then the radius of the arrangement of particles, and that's multiplied by this original skin resistance. So this kind of goes back to what I was saying, is that, you know, this roughness factor increases the skin resistance that already would have been there anyways. So this skin resistance, you were going to have it anyways, regardless of whether the copper was rough or smooth. It's just that this roughness factor increases that and gives you additional impedance. And so if you look at an impedance profile, the impedance profiles of different copper films on a PCB might look something like this. So these are some results that I normally show in one of my digital talks or one of my high frequency PCB design talks. And this just kind of compares some different situations where you are looking at the impedance profile both for the real part and the imaginary part. So the real part is on the left axis, the imaginary part's on the right axis, and here we have a comparison between a smooth line, meaning no roughness, and then a real rough line. And then we took the smooth width and put it into the rough model, just to show a comparison of what happens when you take a smooth line and add in some roughness. And so you can see here, what's really important is these blue lines and then the yellow line. You can see here that the roughness adds in some additional imaginary impedance, and it helps contribute to this waviness that happens in the impedance profile. And that waviness also depends on what happens here in the dielectric constant. So remember, dielectric constants are always a function of frequency. So there's already going to be some waviness in this line anyways. But because the roughness factor is also a function of frequency, that adds additional waviness into this line. Okay, and then you can see that in the impedance spectrum. Now, what's really important is not just the impedance spectrum. I mean, the impedance spectrum is important, but what's really important here is actually in the S parameters. So if you look at the simulated S parameters for this line with a 1 picofarad load capacitance, you can see here what happens to the different resonances that get pulled up from the input impedance along this line. And you can really see how you can appropriately design a line to account for roughness. And so these lines were intentionally designed here to essentially compensate for a little bit of roughness and try and ensure that we don't get too much of an increase in return loss due to the additional roughness. Okay, so the smooth line in this left graph is basically like our perfect line, and then the rough line here, it essentially does add in some additional return loss, and so that's why this curve moves up a little bit. Now, the commercial field solver does basically the worst job here. Here, if you go to the right, you can see also how there's some additional some additional insertion loss. So this is the S21S parameter. And here, when there's some additional loss, these curves move a little bit lower. So this is in dB per inch. Now, if this were a really short line, like let's say you're doing an RF line on, like maybe it's an antenna feed line on a small board, this being in dB per inch, if this is just a couple of inches long, it's not going to be a huge amount of loss that you're going to introduce due to roughness. But if you had a really large board, let's say maybe it's something like maybe it's a specialty RF system. You have to route a line like all the way across the board to get over to an antenna or to a cable, or not a cable, but a connector that's mounted on the edge of the board. All of those losses add up once you get into this range. And we're not at like super high frequency here. What you'll notice is this frequency axis in this graph only goes out to 10 gigahertz. So we'd be dealing right around Wi-Fi frequencies right here where my cursor is. We'd be at 5 to 6 gigahertz Wi-Fi. So that's how the roughness affects impedance, and then subsequently also affects the propagation constant, and then that is all visualized using S parameters as I've shown here in these two graphs. So just going back for a minute, this K factor, what is this K factor and where can I get it? So I'm going to show you that right now. So this is a great 2018 DesignCon paper, and it's written by these guys here, Vladimir Dmitry Zodorov and Bert Simonovich and Igor Kochikov. I'm probably butchering their names, so bear with me. But Bert Simonovich is definitely one of the leaders in this area. And if you go down to page 8, you will actually find all of the important parameters that you need to add in the skin effect roughness, or the roughness to the skin effect, I should say, as I show in the PowerPoint presentation we were just looking at. So there's a lot of information in here, and the Cannonball Hurray model is basically the model that corresponds to this picture here. Okay, you could use the Hammerstad model, but now what people are doing is, instead of using one of these analytical models, what they'll actually do is they'll actually just measure the skin effect So they will measure the skin resistance and they'll get some kind of tabulated data, and then they'll use that instead, and then maybe they can use that to regress to a model like this. So what matters here is if you want to use this model in your own calculations, row 3 is the important row. So this is what gives you that K0 sub S, which is basically the same thing as this K that I have here in this PowerPoint. Okay, so you want to use one of these two expressions. Normally you'd be using this one on the right where my cursor is. Now note here in their definition, they've got a square root 2 here. Okay, so you would also have to include a square root 2 right here if you were defining the change in or the skin effect just using a square root of angular frequency. Okay, so be careful with that and just pay attention to these definitions here, especially here where we have this definition where S is some square, or is I multiplied by this normalized angular frequency. Okay, so here you see the normalized angular frequency is here the standard angular frequency omega, but then it also includes the conductivity, and then it includes the ball radius, so essentially this R value. And so you can use all of that to build this type of model that will generate some results like these. Okay, so if you want to learn more about this, go check out one of my videos on my channel, because I show some examples how to use all of this, and I think you got to be a little mathematically inclined to do all of this, but you can actually then use that to generate these types of S parameters here. The other thing I'm going to do is we'll link to this paper in the description in this video. So go ahead and check out this paper, because it's definitely very revealing as to the math that's involved in getting to these results. Okay, everybody, so hopefully this shows you exactly where copper roughness plays a role in your impedance profile. And if you're using the tools in Altium Designer, it will actually include this copper roughness for you automatically in the impedance calculation that it pulls from the layer stack manager. Super easy to use, super easy to just enter in all your values. Now, last thing to remember, this K value, it's process specific and it's material specific. So it's not like there's one single K value for every microstrip or for every strip line. It really is material system dependent. You can actually measure that based on the roughness data that you can get from a profilometer. You could even do it with an atomic force microscope. There are a number of ways to do it. Thanks for tuning in and watching this video. Go check out Altium Designer to learn more. Go check out Circuit Maker if you're new to PCB design and you want to learn more about using PCB design software. And last but not least, don't forget to call your fabricator about this stuff.